I hope that my lectures related to aircraft performance and flight mechanics have inspired you. Of course, this was just an introduction into the subject, and I could not cover all the topics related to flight mechanics, or more specifically, aircraft performance. So today I would like to give you some insight in which other topics there are in case you continue your studies in aeronautical engineering. Furthermore, you might be curious how aircraft performance calculations are used in real life. Now, let me start with the advanced topics. For this, it is important to understand which fundamental assumptions I have made during all the lectures to simplify the complexity of a complete aircraft. What I did is that I treated a complete aircraft as a point mass. A single point in which all the mass is concentrated, which does not have any inertia, so rotational motion is neglected, and on which all forces act. Now, based on this simple model, I calculated the best possible performance of the aircraft at one moment in time. And this is what we call point performance. Let me give you an example. You can now calculate the maximum steady rate of climb for a given aircraft operating at specific altitude and aircraft weight if you are provided with aerodynamic data and propulsion system data. However, imagine that the problem is not to calculate just this specific condition, but the objective is to calculate the minimum time to climb from sea level conditions just after takeoff to Mach 1.5 at 10,000 meters and the corresponding flying strategy. Now, this is a well-known problem for supersonic military aircraft, and the solution to this particular problem will most likely surprise you. I've tried to visualize it here. In order to get to the final flight condition as fast as possible, the aircraft should first climb at a subsonic speed, then dive and accelerate, then climb and accelerate to a Mach number well beyond the desired Mach number, and finally decelerate and climb to the final condition. Now, the physical explanation of this strange strategy is that the aircraft has a large aerodynamic drag when operating close to Mach 1. And by the way, this is not represented by the lift-drag polar we have been using so far. As a result, the climb performance close to Mach 1 is also very poor. It therefore makes sense first to gain a lot of altitude at a lower velocity and then to quickly dive through the sound barrier by trading off potential energy for kinetic energy. Afterwards, the aircraft can start climbing and accelerating efficiently again. Since the aircraft is accelerating and decelerating, it is in fact an unsteady flight, whereas in the previous lectures we considered a steady flight. So, what you just saw here is an example of path performance instead of point performance. But of course, you can calculate path performance. Before you can calculate path performance, you need to be able to calculate the performance on each point of the path and then integrate it. However, the big question is, what is the most optimum path? Not an easy question at all. So, the minimum time to climb problem is an advanced topic related to the maximum rate of climb problem that you already can answer. Now, there are more path performance problems. For example, you are able now to calculate specific range, which is the distance an aircraft can fly per unit of fuel at one particular moment in time. However, in real flight, aircraft weight reduces during flight due to the fact that fuel is burned. This can be quite significant since about 50% of the maximum takeoff weight can be fuel weight. So, at the end of a cruise flight, the aircraft may have lost half its weight compared to the start of the cruise flight. And as a result, the performance at the end of the cruise is different and the optimal path from start to end needs to be found. Now, in practice, this means for commercial aircraft that it is beneficial to climb gradually during cruise. Exactly the same problem holds for endurance. Now, another part of the mission of the aircraft is takeoff and landing. Now, I have not treated these dynamic maneuvers. What we typically calculate in this case is the distance an aircraft requires for takeoff or landing. Again, this means an integration of the whole path needs to be performed. So far for the difference between point performance and path performance. Another important assumption I made is that there is no wind. Now, you can imagine that wind may affect aircraft performance quite significantly. One particular dangerous example is a microburst. This is an atmospheric condition where for a short duration of time, a pocket of air moves down rapidly through the atmosphere as a result of temperature differences. Now, this can cause quite a hazardous situation if an aircraft flies through it during landing. But don't worry, special systems were developed in the past to ensure safety and to prevent this from happening. So far for the equations of motion. If we consider the vehicle itself, we so far dealt with fixed-wing aircraft. A special topic would be the performance of rotary wing vehicles such as helicopters and tilt rotors. Now, the final aircraft performance topic I should mention is turning performance. We always considered two-dimensional motion with two equations of motion. However, a turn, of course, is a three-dimensional situation which requires additional equation of motion. Typical turning performance metrics are the minimum time to turn and the minimum radius of a turn. And in all these examples, the aircraft can still be approximated as a point mass. If we are, however, interested in the motion of the aircraft around its center of gravity, we cannot make this assumption and should approximate it as a rigid body with an inertia. Now, this representation is important for stability and control calculations, the topic of flight dynamics. And the time scale considered in flight dynamics is much smaller than our aircraft performance calculations. For example, a cruise flight takes several hours and the climb several minutes, whereas the motions considered in flight dynamics, as indicated here, are in the order of seconds. Now, I hope this gave you an impression of some more advanced topics. Nevertheless, the calculations you are already able to do are already very relevant and widely used in real life, mainly for two applications. First of all, the optimal performance for existing aircraft must be calculated for all possible flight conditions. This knowledge can be written in a flight manual, such that the pilot can simply look up in a simple book how to get the best performance out of his or her airplane. Now, this information can also be used in a flight management system by the autopilot. Now, the second application is aircraft design. If we design a new airplane, we can use the aircraft performance calculations to determine the effect of a design change on the aircraft performance. Now, let me give you one simple example. Let's say we have an aircraft that can climb at 5 meters per second, where the excess power, power available minus power required, divided by the aircraft weight equals 5. Now, we might have an idea for a new structural design of the fuselage, which will reduce the total aircraft weight by 5% without changing its shape. Now, by now, you should be able to calculate the effect of weight on power required. Thus, with the equation I just mentioned, you can calculate the change in maximum rate of climb. So, performance calculations are of importance during conceptual design. Now, you've just seen a whole range of new topics and applications. Unfortunately, I did not have the time to give you lectures about all these topics. However, I do hope that it has made you curious and inspires you to learn a bit more about aeronautical engineering in the future.